Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be continuing our lecture on electrostatics and magnetism, and we've made it to the third objective, which is titled Electric Potential Energy. Electric potential energy is the energy stored in a system of charges due to their relative positions. It depends on the positions of these charges with respect to one another, as well as their magnitudes. Electric potential energy, this is just a form of potential energy that arises from the electrostatic forces between charges. And just as gravitational potential energy depends on the relative positions of masses, electric potential energy depends on the positions of charges within an electric field. The formula for electric potential energy between two charges is shown here. U is the electric potential energy, and that's equal to K, Coulomb's constant, multiplied by the magnitudes of the two charges, and that's all divided by R, which is the distance between them. From this equation, we see that the electric potential energy between two charges is proportional to the product of the charges and inversely proportional to the distance between them. Now, as a note here, I want you to remember that work and energy, they have the same unit, the joule. So we can define electric potential energy for a charge at a point in space in an electric field as the amount of work necessary to bring the charge from infinitely far away to that point. Because we know the equation for electric potential energy, and we know the equation for work, that's equal to force multiplied by displacement multiplied by cosine theta, we can go ahead and work from there. We're going to say that D is defined as the distance R that separates two charges, and we're going to assume that force and displacement vectors are parallel, so cosine theta is going to equal 1. With that simplification, we can write that work is equal to the force multiplied by R. And from there, we can replace force with our equation for Coulomb's law. So we have our equation from Coulomb's law multiplied by R, and that gives rise to our equation for electric potential energy. Now, the sign of the potential energy also gives us insight into the nature of the interaction. If the two charges are like charges, both positive or both negative, the electric potential energy is going to be positive. In this case, the charges repel each other, and the energy must be expended to bring them closer together, which corresponds to an increase in potential energy. On the other hand, if the two charges are unlike charges, one positive and one negative, then the electric potential energy is going to be negative. This indicates that the charges attract each other and energy is released as they move closer together, and that corresponds to a decrease in potential energy. In summary, electric potential energy is essential in understanding how charged particles interact within electric fields, and it explains, or it helps explain, the behavior of systems like atoms, molecules, and even large-scale systems like electrical circuits. Now, with that, we're going to jump into a practice problem before we move into our next objective. This problem says, if a charge of plus 2e and a charge of minus 3e are separated by a distance of 3 nanometers, what is the potential energy of the system? Note that E is the fundamental unit of charge, and it's equal to 1.6 times 10 to the negative 19 Coulomb, and K is the electrostatic constant. It's equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Now we're given all of the information we need to plug into our equation for potential energy. We're given Coulomb's constant, we're given the magnitudes of the two charges, and we're given the distance between them. So all we have to do is plug into this equation and calculate. Coulomb's constant is equal to 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. This is multiplied by the magnitude of the first charge, which is plus 2e. So this is going to be 2 times e, which is 1.6 times 10 to the negative 19 Coulomb. And then that's multiplied by the magnitude of the other charge, minus 3e. So this is going to be minus 3 times 1.6 times 10 to the negative 19 Coulomb. What you're going to notice here in the numerator is that Coulomb is going to cancel out. Then this is divided by the distance between them, which we're told is 3 nanometers. We want this to be in units of meter so that it cancels out with this meter unit that's part of our electrostatic constant. So we're going to write this as 3 times 10 to the minus 9 meters. What we're going to be left with in terms of units is newtons times meter. And so this gives us our familiar energy unit of joule. Now, if we plug this into a calculator, we're going to get minus 4.6 times 10 to the minus 19 joules. And that's how we solve this problem. Now we can move into our fourth objective, titled electric potential. Now that we've discussed electric potential energy, it's important to understand a related but distinct concept, electric potential. While the two terms may sound similar, they're not the same thing, and we want to understand the difference. Electric potential, this is defined as the ratio of the charge's electric potential energy to the magnitude of the charge itself. In other words, while electric potential energy refers to the energy stored in a system of charges due to their positions, electric potential tells us how much potential energy exists per unit charge. The formula for electric potential is shown here. V is the electric potential measured in volts. It's equal to U, which is the electric potential energy, divided by Q, which is the magnitude of the test charge. This is also equal to K, Coulomb's constant, multiplied by the source charge, divided by R, which is the distance between the test charge and the source charge. Now I want to make note, we said electric potential is measured in volts. 1 volt is equivalent to 1 joule per Coulomb, meaning that electric potential quantifies how much energy is associated with each Coulomb of charge in a given location. Now, to clarify the difference between electric potential and electric potential energy, let's consider an example. If we have a positive test charge placed near a positive source charge, the test charge will have a certain amount of electric potential energy due to the repulsive force between the two charges. On the other hand, the electric potential at any given point around the source charge is independent of the specific test charge you place there. It only depends on the position and the magnitude of the source charge. So, while electric potential energy depends on the specific charge you're considering, electric potential describes the energy available to any charge placed in that location. Now, it's also useful to understand how electric potential relates to other quantities in electrostatics. This table here serves to summarize and organize a lot of the information that we've covered thus far. We've seen that the electric force between two charges is given by this equation right here, where it's equal to Coulomb's constant multiplied by the magnitude of the two charges divided by r squared, where r is the distance between them. We can also express electric potential energy. It's equal to Coulomb's constant multiplied by the magnitudes of the two charges divided by R. Notice that the difference between electric force and electric potential energy is the denominator, R squared versus R. Then we also talked about the equation for electric field strength. This is equal to Coulomb's constant multiplied by the magnitude of the source charge divided by R squared. Notice that the difference between electric force and the electric field strength is in the numerator. For electric force, it depends on the magnitudes of the two charges, but for electric field strength, it just depends on the source charge. Finally, we just talked about electric potential. It's equal to Coulomb's constant multiplied by the magnitude of the source charge divided by R. Notice that the difference between electric field strength and electric potential is in the denominator, R squared versus R. You also notice that electric potential is related to electric field strength and potential energy, but it just provides a different way of thinking about the energy landscape created by charges. And hopefully this table helps you remember the differences between electric force, electric potential energy, electric field strength, and electric potential. Now, an important concept that's related to electric potential is the idea of potential difference, also called voltage. If we consider 2 points A and B with electric potentials VA and VB, the potential difference between these 2 points is given by delta V, and that is equal to VB minus VA, which is equal to WAB. This is the work done in moving a charge from point A to point B, divided by Q, which is the charge being moved. Voltage is fundamental to understanding how electric potential changes in space. It tells us how much work must be done to move a charge between 2 points, or in other words, how much energy is available to be released if the charge is allowed to move between those points. This concept becomes particularly important when we look at electric circuits, where the movement of charge, and thus the voltage between 2 points, drives the flow of current. This is going to be the focus of the next chapter. To summarize, electric potential is a measure of how much electric potential energy exists per unit charge in a particular region of space. It's closely related to electric potential energy, but it focuses on the charge's environment rather than the specific amount of energy in the system. And with that, we can move into our fifth objective. This is going to involve special cases in electrostatics. A key concept to understand here is the idea of equipotential lines. An equipotential line is a line on which the electric potential at every point is the same. These lines give us valuable insight into how electric potential behaves in different regions of space. What's particularly important to note is that electric field lines and equipotential lines are always perpendicular to each other. This is a crucial characteristic that we're going to see across different scenarios. Let's discuss 3 specific cases where equipotential lines are important: constant electric fields, point charges, and dipoles. Let's start with the first scenario, which is equipotential lines in a constant electric field. In systems like parallel conducting plates, such as that found in capacitors, the electric field lines run perpendicularly between the plates. In this case, the equipotential lines are parallel to the plates, meaning that any point along one of these lines has the same electric potential. As you move closer to one plate or the other, the potential changes, but it remains constant along the equipotential line. In these types of configurations, the electric field strength remains uniform between the plates, and the voltage drops at equal increments along the distance. The spacing between the equipotential lines represents this uniformity. The second scenario is equipotential lines around point charges. For a point charge, the situation is quite different. The electric field radiates outward from a positive charge or inward for a negative charge, and the equipotential lines form concentric circles around the charge. Each of these circles represents a surface where the electric potential is constant. These circles form an equipotential surface, and the electric potential decreases as you move further away from the charge. You can think of this like the surface of a sphere. Every point on that sphere has the same potential. The dashed lines in the diagram represent equal voltage increments, showing that the equipotential lines get further apart as the distance r from the charge increases. And the spacing illustrates that the electric potential diminishes more gradually the further you move from the charge. The third case is the electric dipole. A dipole consists of two equal but opposite charges, and they're separated by a small distance. The electric field lines around a dipole, are more complex because of the interaction between the positive and negative charges. In the case of the dipole, the equipotential lines show mirror symmetry about the center point of the dipole. The field lines between the charges, they curve sharply, and the equipotential lines are everywhere perpendicular to these electric field lines. So here are the electric field lines, and here are the equipotential lines around the dipole. Now, a particularly important equipotential line is the plane that lies halfway between the positive and negative charges. This is called the perpendicular bisector of the dipole. At this point, the electric potential is zero. This means that if you place a test charge in this plane, no work is required to move the charge along the plane because the potential is the same at every point. In summary, equipotential lines provide a useful tool for visualizing the electric potential in various charge configurations. Whether you're dealing with a uniform electric field, point charges, or a dipole, these lines help us understand how potential changes in space and how it relates to the electric field. Now we want to focus on electric dipoles. This is an important configuration in electrostatics that consists of two equal but opposite charges separated by a distance d. This separation creates a unique electric field pattern and potential energy behavior, which has numerous applications in both physics and chemistry. So again, an electric dipole results when two charges, one positive and one negative, are positioned a small distance apart. The electric potential at any point in space due to a dipole can be calculated by considering the contributions from both charges. If we place a test charge at point P in space, the total potential at P is the sum of the potentials due to the positive and negative charges. The electric potential V at point P due to a dipole is given by this equation that we see here. V is equal to KQ over R1 minus KQ over R2. R1 and R2, these are the distances. R1 specifically is the distance from the positive charge to point P, and R2 is the distance from the negative charge to point P. K is Coulomb's constant, and Q is the magnitude of the charges. Now, by simplifying the equation for points relatively far away from the dipole, we can actually express the potential in this way. V is equal to KQ multiplied by R2 minus R1 over R1 multiplied by R2. Because R1 and R2 are very close to each other for points far away from the dipole, we can approximate the potential further for points that are at a distance compared to the dipole separation. For points in space that are relatively distant from the dipole, the electric potential, it can be written in this manner. Here we see that V is equal to KQD over R squared cosine theta. D is the separation between the two charges. Theta is the angle between the position vector and the axis of the dipole, and R is the distance to the point from the dipole. Now, this approximation shows us how the electric potential of a dipole decreases with the square of the distance from the dipole. Now, unlike the potential of a single charge, which decreases as 1 over R, the potential due to a dipole falls off more rapidly as 1 over R squared. Now, a key concept in understanding dipoles as well is the dipole moment. This is represented by P, and the dipole moment, this is a vector quantity that points from the negative charge to the positive charge, and it's given by the formula P equals QD, where Q is the magnitude of either charge, since they're equal in magnitude but opposite in sign, and D is the distance separating the charges. The dipole moment P, this is a measure of the strength of the dipole, and it plays an important role in how the dipole interacts with external electric fields. The larger the dipole moment, the stronger the interaction with an external electric field. So in summary, the electric dipole creates a distinctive electric field and potential that depends on the arrangement of the two charges and the distance from them. Now we can better understand this by tackling a practice problem. So let's do this one together. This problem says the water molecule has a dipole moment of 1.85 dBi. Calculate the electrical potential due to a water molecule at a point 89 nanometers away along the axis of the dipole. We're given Coulomb's constant, 8.99 times 10 to the 9, Newton times meter squared per Coulomb squared, and we're given the conversion from dBi to Coulomb times meter. 1 dBi is equal to 3.34 times 10 to the minus 30 Coulomb times meter. Now, the equation we want to use to calculate electrical potential is V is equal to KQD over R squared times cosine theta. Remember, we want to calculate the electrical potential due to a water molecule at some point away along the axis of a dipole. So this is going to be the equation we want to use. Now, because the question asks for the potential along the axis of the dipole, the angle here, theta, is going to be equal to 0 degrees, and cosine 0 is equal to 1. So really, the equation we're dealing with is just this part right here. We're given K in the problem. This is Coulomb's constant. We're also given QD. We're told that the dipole moment is equal to 1.85 dBi. Dipole moment P is equal to QD. So this QD value is equal to 1.85 dBi. And we have the conversion to change it from dBi to Coulomb times meter so that the units appropriately cancel out with Coulomb's constant. And then we're also given R, 89 nanometers away. We also want to convert this to meters so our units match up and cancel out appropriately. So let's go ahead and start to plug values into this equation. V is equal to 8.99 times 10 to the 9 Newton times meter squared over Coulomb squared. This is going to be multiplied by our dipole moment, QD, 1.85 dBi, and we want to go ahead and convert this to Coulomb times meter. 1 dBi is equal to 3.34 times 10 to the negative 30 Coulomb times meter. So this is our numerator. This is all going to be divided by 89 times 10 to the minus 9 meters, and this is squared. Now to do this calculation, we're going to go ahead and do a couple of approximations. I'm going to approximate this to 9, I'm going to approximate this to 2, and I'm going to approximate this to 3. And then I'm going to take these values and I'm going to put them near each other, 9 times 2 times 3. Then I'm going to take these values, 10 raised to some value, and I'm going to combine these together. We have 10 to the 9 and we have 10 to the minus 30. To do this, it's just going to be 10 to the 9 multiplied by 10 to the minus 30. This is just an addition of these exponents. So 10 to the 9 plus negative 30. This gives us 10 negative 21. So this is our numerator. Now, what about our denominator? I'm going to round this to 90. And actually, I'm going to rewrite this whole part a little bit differently. Instead of 90 times 10 to the minus 9, I'm going to write 9 times 10 to the minus 8. All right, this is going to be our denominator. Those are absolutely equivalent. 9 times 10 to the minus 8, and this is squared. Okay, now what I'm going to do is I'm going to expand the denominator. I'm going to write it in a different way so we can cancel out a couple of these variables here. I'm going to keep the numerator as is, 9 times 2 times 3 times 10 to the minus 21. And then in the denominator, remember 9 times 10 to the minus 8, this is squared. So the squared value goes to both of these quantities. So we have 9 times 9, and I'm going to write it in this way. You'll see why in 1 second. And then I'm going to write 10 to the minus 8 squared. That's just 10 to the minus 16 now. Now we can see that this is the best way to write it because these 9s cancel out. All right. And then what we're left with here is 2 times 3, 6 divided by 9. And then we can deal with these 10 to the powers in a very easy way. When we have 10 to the negative 21 divided by 10 to the negative 16, we are essentially just subtracting the 2. So what that means is we have 10 minus 21 minus negative 16. This gives us 10 negative 5. So what we're left with is 6 over 9 multiplied by 10 to the negative 5. We can simplify this further. This is 2 over 3 multiplied by 10 negative 5. And this is equal to 0.66 times 10 to the negative 5, or in other ways, 6.6 times 10 to the negative 6. And the units here is volts. So this is our answer for the problem. Now, if you were to plug it into a calculator, you're going to get a value that's pretty close to this. The actual value is 7.01 times 10 to the negative 6 volts. With that, we've solved this problem, and we can move into our next topic. One particularly important feature of the electric dipole is the perpendicular bisector, which is the plane that lies exactly halfway between the positive and negative charges. This plane has a unique property, and that property is this: the electric potential at any point along the perpendicular bisector is exactly 0. And this occurs because the angle between the plane and the dipole axis is 90 degrees. And since cosine 90 degrees is equal to 0, the potential, which depends on this term, is 0 along this plane. The electric field, however, is not 0 along the perpendicular bisector. In fact, the magnitude of the electric field at any point along this plane can be approximated using this equation right here. E is equal to 1 over 4 pi epsilon naught multiplied by P over R cubed. P is the dipole moment, R is the distance from the center of the dipole, and epsilon naught is the permittivity of free space. The electric field vectors At points along the perpendicular bisector, they point in the direction opposite to the dipole moment vector P, showing that even though the potential is zero, the field still exists and it points away from the dipole axis. Now, our final topic in this objective is dipole torque. The dipole serves as a classic example of a system upon which torque can act, and understanding how this works is critical for analyzing the behavior of dipoles in electric fields. Torque is a measure of the rotational force that can cause an object to rotate around an axis or pivot point. In the context of a dipole, torque describes the rotational effect an electric field has on the dipole's orientation. In the absence of an electric field, a dipole can assume any random orientation as there's no external influence to dictate its direction. However, when we place an electric dipole in a uniform external electric field, things change. The charge in the dipole, each charge in the dipole, being equal and opposite, will experience a force exerted by the electric field. The positive charge will experience a force in the direction of the electric field, while the negative charge will experience a force in the opposite direction, kind of like you see drawn here. These forces are equal in magnitude, but opposite in direction. This creates a situation of translational equilibrium, meaning that the net force acting on the dipole is zero. The dipole does not move from one position to another. However, because the forces are acting on two different points in the dipole, separated by a distance d, there is a net torque about the center of the dipole axis. The torque on a dipole in an electric field, it can be calculated using this equation right here, where tau is torque. This is equal to P, the dipole moment, multiplied by E, this is the magnitude of the external electric field, sine theta, where theta is the angle between the dipole axis and the direction of the electric field. This equation tells us that the torque depends on both the strength of the electric field and the dipole moment, as well as the orientation of the dipole relative to the field. When theta is 90 degrees, the torque is at its maximum because sine 90 is equal to 1. In this case, the dipole will experience the greatest rotational force, trying to align it with the electric field. Now, the effect of this torque is to rotate the dipole until it is aligned with the direction of the electric field, where theta is equal to 0 and the torque is equal to 0. At this point, the dipole is in rotational equilibrium, meaning that no further rotational force is acting on it. In summary, torque acts on a dipole in an electric field, causing it to rotate until it aligns with the field. And with that, we've completed Objective 5. I'm going to go ahead and end the video here. In the last part of this lecture, we're going to go over Objective 6, which covers magnetism. I hope that this has been helpful thus far. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.